be one too many processes for this poor little hard drive to deal with. All right. So entropy, disorder. I would like you to think about my desk. What happens to it naturally? You've seen my desk over the course of the year last year. What happens to it over the course of the day? More messy, more stuff, just more chaotic, yes? That's the natural way things go. In order to make it go the other way, I would have to do some, what? Where? Yes? So I think it was Nathan who was asking me the other day and saying, well, once you get to products, if the products are more stable, like if they have lower enthalpy, why on earth could you end up with a reversible reaction, right? Like, why would it want to go backwards? It's more stable over here. Well, the answer is that if it's more random and disordered over here, then you have two forces opposing one another. You've got one pushing forwards, one pushing back, and so you'll end up with an equilibrium between the two. Does that make sense? Kind of? Don't worry, we got like a whole section on entropy and enthalpy. This is just like mentioning it, okay? So if you're like, I don't know, don't worry. Still trying to scroll the wrong way. Okay, so you'll notice that in this particular example that we have here, the concentration of the reactants, there's not very much, and the concentration of the products, there is a lot. But the two rates are equal, so we are at equilibrium. And I'm going to introduce you to a concept next day after your test, which is called KEQ, which is the equilibrium constant. The KEQ. And we're going to find out that that value is equal to the concentration of the products divided by the concentration of the reactants. So that's a ratio, yes? So if I were to make the amount of products greater by, say, adding in some extra products, the system will actually shift so that the ratio goes back to what it was before. Does that make sense? Okay, so the ratio between products and reactants always stays the same unless we have a temperature change, but we'll talk about that later, okay? Talk to Mr. What's his name at break, Mr. H. Okay, so under different conditions, right, maybe I increase the temperature or maybe I decrease the temperature, I don't know which. At equilibrium, under different conditions, say at a different temperature, you might have at equilibrium more reactants than products. And that's fine, it's just a different set of conditions, yes? But if you don't change the temperature, that ratio will remain the same. The moment you change the temperature, you can get a new ratio, okay? Summary, just because the concentration of reactants and products remain constant does not mean that the product's concentration equals the reactant's concentration. That is a huge misconception. Yes? People like to think that. They're like, oh, it's equilibrium. The concentration of reactants and products must be equal. They do not. So let's learn some language around this. If we have more products than we do reactants, we say that the position of the equilibrium lies to the right. And usually we will say that the products are favored. Okay, that's the language we use around that. If we have more products than reactants, the products are favored. And by favored, we mean thermodynamically favored. Yeah? If we have more reactants than products, then the position of the equilibrium lies to the left, and we would say that the reactants are favored. We have more reactants than products. Now, let's take a look at this. Adding heat to the system, in this particular case, favors the forward reaction. And when we say favors the forward reaction, that means that the forward, yes. 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 You will look at the KEQ value. If KEQ is greater than 1, the products are favored. Because you have a larger number on top of a smaller number. If you have a KEQ less than 1, and you'll get these numbers from various places. There are tables, or you can do calculations around them. And then if it's less than 1, that means you have a fraction, yes? Which means you have a smaller number on top of a larger number. So if KEQ is less than 1, the reactants are favored. Sorry, that should say ED here. Because what we do is KEQ is equal to the concentration of products over, and in this case, the concentration of reactants is smaller. Yes? If KEQ is greater than 1. If KEQ is equal to a large amount of reactants on the denominator and a small amount of products in the numerator, you're going to have a KEQ less than 1. Is good? Cool. That was a good question. Now, in this case, this is not always true. An increase in temperature favors the forward reaction. That means, what do you think that means? That means that the forward rate is going faster than the reverse rate. So if you have a stress, remember, a stress is something that we do to the system. If we stress a system, we will be changing the rates. Now, I'd actually like you to think about this for a moment. If we increase temperature, what's going to happen to the forward rate and why? If we increase temperature, what happens to the forward rate and why? Explain it to your partner. So if we increase the temperature of any reaction, what happens? We do what? We increase the reaction rate. Why? 2 reasons. Tell your partner what those 2 reasons are. Collision theory. This is for tomorrow's test. Okay, so the particles collide more frequently, but what else? A higher percentage of those collisions have sufficient energy for a reaction to occur. Yes, so we have increased the forward rate. So we could draw our arrow as being now bigger, yes? What have we done to the reverse rate when we increase the temperature? Tell your partner, what have we done to the reverse rate when we increase the temperature? Okay, you're going to vote on this. You're going to vote either the reverse rate increases or the reverse rate decreases. Are we ready? 5, 4, 3, 2. And you can be like, I don't know, that's fine too. Okay, so you can be like, the reverse rate is going to increase when we increase temperature. The reverse rate is going to decrease when we increase temperature. Or, I don't know yet. This is confusing so far. Okay, and that's a perfectly valid answer at this point. All right, 5, 4, 3, 2, go. All right, I got some I don't knows, I got some ups, I got some downs. Now, if we increase the temperature, what happens to the speed of the particles? The particles move faster. If the particles are moving faster, what happens to the number of collisions? It increases. It doesn't matter whether it's reactants or products, it will still increase. And what happens to the percentage of effective collisions? It will also increase. So what has happened to the reverse rate? The reverse rate has increased. But the forward rate is faster than the reverse rate. How is that possible? Which one increased more? The forward rate increases more. When we heat it, both rates increase. In this particular case, and I'll tell you how to tell how in a little bit, okay? In this case, the forward rate increases more. And that's why the forward rate is faster than the reverse rate. So if we draw our increased rate, there's our forward rate has been increased. Our reverse rate has also been increased, but not by as much. Is good? Okay. And so what will happen is that you will end up with a new equilibrium. What can you say about the forward and the reverse rate after, like, we've now got the forward rate going faster than the reverse rate? Eventually, we're going to come to a new equilibrium. What will be true of both rates at the higher temperature? They will both have increased. So what's going to happen is you're going to get, they're equal. The forward one becomes faster, the reverse one becomes a little bit faster. And then eventually they kind of, I can't make my arms like more than 2 different sizes, but you kind of get the idea. If they're kind of slopey, that's like kind of medium. They both end up medium faster. This one went really faster, this one went a bit faster. They both end up medium faster. Is good? Okay. So we're now at a new equilibrium. And both rates are medium faster. Okay. Now, removing heat from the system, like let's say we put this thing in an ice bath. So we are now removing heat. It favors the reverse reaction. What does it mean if it favors the reverse reaction? Which rate is faster? The reverse reaction is faster than the forward reaction. Which rate, what's going to happen to both rates when we cool the system? When we cool the system, both rates will slow. If they both slowed down by the same amount, would the equilibrium shift? Would we end up with a new position? Would we end up favoring the reactants or the products if they both decreased by the same amount? No. So both rates slow down. Which one had to have slowed down more? The forward rate had to have slowed down more in order for the reverse rate to be faster than the forward. So we're going to say, okay, my forward rate slowed down more, and my reverse rate slowed down, but not as much. And the reverse rate slows, but not as much. All right, so eventually the forward rate is going to increase until it's equal with the reverse rate. They'll now be equal, but they'll both be slower than they were before. And I'll let you know right now that from this, I can tell that the forward reaction is the endothermic direction, because changes in temperature affect the rate of endothermic reactions more than the rate of exothermic reactions. Not forward reaction, endothermic. So if you heat up a reaction, whichever direction is endothermic is going to speed up more than the exothermic direction. If you cool a reaction down, the endothermic reaction is going to slow down more than the exothermic reaction. And it has to do with the fact that the endothermic reaction has a higher activation energy than the exothermic reaction. We will look at that more another day, but we have like 3 minutes left. So we're just going to get through as much of this as we can, and then you're going to go home and make sure you're ready for your test tomorrow, okay? So what is shifting? We've talked about this a little bit. I sort of mentioned it in passing, but this is a hugely important word. It's a vocab word, along with one side being favored or the other side being favored, along with the word stress, which means something we do to a system. The term to shift, it is the response of an equilibrium to a stress. So a system is said to shift when it moves from one equilibrium position say with the products favored, to a second equilibrium position, say with the reactants favored, or maybe just the products favored but not as much, or with the products favored more, okay? So that would be like going from this situation where we have the products favored to this situation where we have the reactants favored. Systems shift in response to a change in conditions. What do we call that change in conditions? That's called the stress. And we'll talk about all the things that are stresses and aren't stresses another day. While a system is shifting, what's going to be happening to concentrations? Will they be staying the same or will they be changing? They will be changing. So while it is shifting, the concentrations will change. Once a system is finished shifting, what happens to the concentrations? The concentrations remain constant because we have established a new equilibrium. Okay?